kinetic graphs. And we will start off with this physics demo application. And the reason why we start with this one is because, well, these are graphs, more or less. They have nodes or vertices, they have links or edges. Now they also have some kind of fancy properties like physics or whatever associated with them. But the reason why I start with this, we won't use physics today, at least almost not at all to this extent. But I will reuse most of the code for making today's application. So, yeah. Okay. So I will start by renaming the document. So today we are going to play with graphs. And I call them kinetic because they are going to move somehow. And we will have one canvas for now, but I won't have any click effects. So I'm going to remove this notice from here. And I'm going to remove the mouse down listener, so we won't interact with the graphs. I just want to display graphs today. I won't need also the get nearest segment function that was doing something before, but I will use the segment class and I will use the particle class because they will more or less be edges or links, how you want to call them. And particles will more or less represent vertices or nodes. So different terminology, you will find them being referred to in different ways. Dots and lines can also be something. Okay. Now, this simulate physics, I'm going to rename this function because there won't be much physics involved. I'm going to say animate graphs on canvas C. Okay, and I have to rename also the function itself. This one is doing very many hard-coded stuff here, drawing that humanoid creature and whatever pendulum was on top. I'm going to just delete everything there. So, yeah. And then in the interval, we were doing many complicated physics-related things. First, updating the location of particles according to their velocity. And then we were applying constraints so that they cannot escape whatever segment boundaries were there. I'm going to comment out this applying constraints entirely. We won't use such complicated physics today. And then here I was checking if particles are going out of the screen, and I was not allowing them to go out of the screen. Let's maybe keep this and see what happens. And then particles segments are being drawn here. Yeah. Okay, as you can see, 1, 2, 3, 4, 5, 6, 7 indents. This is not nice because see what is happening here. I'm starting to get broken lines and problems all the time. These can be always replaced with function calls. So instead of having update location of particles, you just write update location of particles. And you make a function with that. And then this will just run inside that function, which is defined back there at a nice level. And this one will not have these extra indents. So definitely do that when coding. Maybe we also try to do it if time today, but yeah, so this is one thing. This here can be keep particles on screen, and the same function would apply there. It would adjust their location. So separate the code, make it modular. This is not a mess because I am having some comments and I try the code to be understandable by giving proper names to variables, but it can be much better if more time to polish these things. Okay, so what are we gonna animate here? Let's say a graph with n is equal to 50 nodes. And let's make them random. So 50 nodes, meaning 50 particles. And this needs a location vector and a velocity vector, the particle constructor. So our location, let's have it random. So multiplying this by the canvas size gives me a value between 0 and 300 for today. And our velocity, let's leave it 0, no velocity. Okay, and I'm gonna push the particle to the particles array, right? Okay, so this should work if I didn't delete something by mistake that should have been there. So let's see, refresh the page. Okay, gravity is still on. So I was expecting the particles to just stay there, but they don't. Gravity is still there. Let's remove the gravity. So I'm not gonna add the gravity vector to this location. Amazing. They are not moving at all, but let's make them move somehow chaotic, like changing speeds, changing directions all the time. So instead of using the gravity value here, I'm gonna say add vectors a random vector here. And I have to define it. So I'm gonna say math random minus 0.5 because I want them to move both directions, plus, minus. So math random between 0 and 1. Doing this is between minus 0.5 and 0.5. And same for the y component. Let's see now what happens. Something happens.
How come they still stay inside the screen?
Because of this code here.
Oh.
Yeah.
So when they hit the screen, they...
When they hit the screen, they are not allowed to continue off the screen. So the reason why they come back is because of the random velocity eventually changes.
Okay.
Now you can see they tend to stick to the sides of the walls. This is because they have a velocity, maybe it increased by several pushes. And then when they touch the wall, they still have this velocity that somehow needs to be taken back by some other random effect. So I'm kind of happy with this movement. Maybe it's a little too fast because, yeah. I always forget because I see things very rapidly here, but on these boards, I'm going to slow them much down. So our random vector is going to be scaled by 0.2. Let's scale it by 0.2, and now the random vector is not going to be so strong anymore. So let's see. A little better, maybe even 0.1, so that you can understand better from this. Yeah, I think now you should get a better understanding of movement, like which point moves where, more or less. Okay, so we have the vertices. Let's add links. That's the whole point of today. And when we talk about links and about graphs, of course you maybe have some links coming from real data, like relationships in social networks, or I don't know, anything. But if you want some artificial data, probably one of the simplest type of graphs that you could generate is the nearest neighbor graph. So connecting each point to whatever its nearest neighbor is going to be, or his nearest neighbors. Maybe you want to have more links, so then you accept two links per node, or whatever, or 3 or 4. So let's see how that one looks like. Well, more or less, if this would be some kind of points on the space, A's nearest neighbor is B, B's nearest neighbor is A, C's nearest neighbor is D, and D's nearest neighbor is B?
A.
Well, it's B. A is farther away. Well, anyway, and then second nearest neighbor of A is...
Something happened.
Oh. Okay, can you still see in Kuopio?
Yes, we got it.
Okay, good. So now, what is the second nearest neighbor to A?
D.
Yeah. And the second nearest neighbor to B? Yeah. And the second nearest neighbor to C?
B.
B, because D is already there. And for D,
A.
A or C, they are quite close, but I
A.
think C is a little bit closer than B. You can see that this graph is actually not symmetric. Today we will consider them symmetric. So if you have two links there, I'm just going to draw two lines on top of each other, and it will look like one line, maybe slightly thicker because of this canvas effect. But in practice, people also tend to combine these relationships, but you can see they are asymmetric. So in practice, you maybe have a best friend, somebody, but that best friend maybe has some best friend that is not you. So
Impossible.
it's very possible. So yeah, best friends is something strange. Okay. Yeah, so this is now what we are going to try to do. We don't have any segments as of now anywhere, but every time these particles move, I want to create the segments equal to get KNN links or segments, or how you want to call them. Let's use links because it's proper graph terminology. Segments refers to visual. When I'm displaying the link, it looks like a segment, but links are hypothetical things. You can have graphs in high dimensions where you cannot draw the links in high dimensions. So segment just means the visual thing. So get KNN links for the particles, and let's set the K value of 2. So similar to my drawing here with also the blue links added there. So I'm going to now write a function for that. get KNN links, the graph basically, for a set of particles and with a given K value. Now this is maybe going to get a little bit complicated, but I hope it won't. Let's see. I hope it's gonna come out nice. So, for each particle, so for every particle, I want to get the neighbors of that particle. Get neighbors of particle I. I'm going to send the index. I'm going to send also the list of particles where to look for. And how many neighbors I'm going to get? K. So once I have the neighbors, I'm going to add them to segments. I maybe don't use a global variable here because I want to maybe draw multiple type of graphs at the same time. So I'm going to need different graphs, and I'm going to keep local variable here. So the segments are constructed by two particles. That's what is happening in the constructor. And here we're going to go through all the neighbors. And we're going to say segment is equal to new segment of our initial particle, the I particle from here. So a line between this initial particle and each neighbor that we are getting here, so neighbors of J, is going to be that. So these neighbors are actually neighbor particles. It's going to be the same instances of the same class, more or less. Okay, and then I'm going to push this segment into this segments array, and at the end I'm going to return the segments. So here get KNN links is going to update my currently global variable with whatever results are coming from this KNN links. And these links for every particle, a segment connecting it to all its neighbors, which we still don't know. We have to calculate the neighbors somehow. So this function, we don't have it yet. Okay, so let's write it. So get neighbors of the particle at index, given index, in this case I here at the top, from the list of particles, and I want to get k neighbors. Okay, first step what I'm going to do here is calculate distances from my index particle to all other particles. So it's going to be, the nearest neighbors are going to be the ones with the smallest possible distances all the time. So I go through all particles, and I say here I'm going to add an attribute to this particles object. I'm going to say particles of I dot distance, dist for short, is equal to distance between particles of index and particles of I. And because this expects a vector and particles is a particle, I need to specify here location. So the location of particle at the index and distance to the location of every I particle there.
going to also get the location between him and himself?
Very good point. Very good point. So the index particle is going to have a distance of 0. It depends now how you want to handle this. Do you want to consider each particle its own neighbor? It's a little bit theoretical concept here, and it won't look like anything. It's just going to be a line to itself. So then to really have lines appearing, you would need to have a k equals to 2, which is not very natural. So you could, for example, do some tricks, like if I is the index, you could say that the distance could be, for example, infinity. This will not put your particle anywhere near itself. So it will be the last choice. But in the last choice, if you put k equal to n to the number of points, then you have a complete graph, all possible links appearing there. So this will more or less never be linked to itself. It's meaningless to try k and n if you're going to connect everything anyway. Otherwise, we could handle this in this way. So now the smallest distance is going to be distance to something else. It could be 0. There could be another particle overlapping exactly on top of the current particle, but not itself. It's not going to be considering itself. So, very good point. Okay, so now we have distances to the particles, but we should also get a limit to the nearest distances that we have, the nearest k distances. Now, one very general approach here is to sort. Sort all the distances in increasing order, and then threshold to the first k. We are going to do that, but it's not very efficient if you consider maybe if you want just 2nn or 3nn. If this would be, if you know that you only need 2nn, then just find the minimum and then find the minimum again. It's going to be a linear time search. Sorting is,
N squared.
well, it's n log n. Or n squared depending on the implementation. I'm going to implement insertion sort now, but you can use any sorting algorithm here. I'm going to implement a variant of insertion sort that doesn't change the order of the particles. It's just going to output me the new results. So let's say here neighbors, new order, an empty array. And what we are going to do now is go through this particles list, which now have distances associated with them. And we're going to say here j equal to 0. Actually, these neighbors, it can be initialized with something already. We could initialize it with the first particle. And then we can start here with the first particle, because insertion sort always looks in this array from the beginning to the end. It assumes that this array is always in order. So if it finds something with a greater value than whatever is at the current index, if we go in order in it, it means that everything on the left was smaller and everything on the right is bigger. So it needs to shift elements to the right and insert it in the middle. So first I have one element there, and then I'm going to try to insert the rest n-1 elements into that. And for that you need a while loop, at least that's how I wrote it here before. So more or less simulating a for loop. So while we are iterating through this neighbors array, so this is going to have a j++ here, but also while our distance, whatever distance we are looking at the moment, is greater than the distance that we are, the distances that we are traversing in the neighbors array, then we just traverse the neighbors array. And this while will stop at the end, assuming you have a distance with very, very high value, you're going to just stick it at the end. So when your j is going to be neighbors.length. But it may also stop if you just found a value that exceeds the current one in the neighbors array, but is less than the one that is following. So more or less you found a place in the neighbors array where it needs to be squished in the middle. So all the elements go a little bit to the right and one new element goes here at the j. Yeah, I think so. So JavaScript has this nice function here, this splice. I already used it some time ago for removing elements. So if I write this, it would remove one element from position j. I don't want to do that. I want to remove 0 elements . Okay, I want to remove 0 elements from the neighbors array, but I want to add the ith particle at the j location, which is either the end of the neighbors or the place in the neighbors where this new number fits in. So this is how insertion sort could look in JavaScript, even though I think there could be even better ways to implement that. And now that I think about it, selection sort would be even better, because that one you can stop after k iterations. So if you stop selection sort after k iterations, you have a guarantee that the first elements are going to be the minimum k. So it would do less work than insertion sort. This is to help you with DAA if you are taking DAA. Okay. So now we get our neighbors. Let's return them. And save the file, refresh the page, and hope for a miracle. Yay! I'm not limiting them in any way. So more or less I'm drawing a complete graph. So this is how a complete graph looks. All the neighbors from all the points are connected to all the neighbors from all the points. So one way to limit this is just a loop here again. So while our neighbors dot length is greater than k, we can pop from that array. So pop removes the last element of that array. So this is a sorted array. The first neighbors should be the nearest neighbors. And if I'm going to just remove the further away neighbors until I get to the value k, then this should be just good. I save the file, refresh the page. I think this looks good. So more or less points are moving, and as they are moving, the segments are reconstructed so that you always connect the two neighbors at each frame of the animation. Maybe the movement is still a little bit too fast for this system, so I'm going to have an even softer moving force. So this is some kind of effect that I have seen on different websites that they put, for example, on the background. It's a nice thing to do because you don't need any images. Okay, so of course you could put a GIF, how you want to call it, animation on the background, but this one, it's all code and no megabytes. It's also random, it doesn't loop. It can be interesting, we can make it maybe more interesting. Let's try to have instead of two. Okay, let's have a break. One question I got during the break is, it would be nice if this graph would be always connected. So for example, here you have this connected component separate from all the other things. If it would be connected, then it would look somehow like a network, like everybody is linked to everybody somehow with some degrees of separation. So one way to do that, to have a higher connectivity, is to increase the number of K. And that's what we're gonna try to see how it looks like. But what I'm gonna do is I'm gonna make more canvases. So let's prepare 2 more canvases. Let's have canvas A, canvas B, canvas C again. And here we have canvas A, canvas B, and canvas C. And my animate graphs function should have all of them here. I mean, I'm gonna animate graphs on all 3 canvases at the same time. And what I'm gonna do in the animate graphs function, first of all, I don't really need this segments global variable here. Particles can be, but even that I don't really need it. So I'm gonna remove it just for simplicity. And here where we are calculating the segments, I can have a local variable. So I could call them KNN2 segments, but I'm just gonna say segments A, because segments A will go to canvas A. So segments A, segments A, segments A. I do have to check this canvas variable, so this one, it's canvas A, and now also canvas B and canvas C. Okay, here we clear canvases. Let's just clear all of them. And yeah, this is where the drawing happens. So let's put the particles on canvas A, segments A on canvas A, but I can also put the particles on canvas B and canvas C. So I'm gonna have 3 canvases, the same exact particles on all of them, but the segments A coming from the KNN2 graph are gonna be on the first canvas only. And now I could control here segments B. Let's say KNN is equal to 3. Let's put also segments C. KNN is equal to 10. We'll have some different results there. And I'm gonna do the same for these, draw the other segments as well. So segments B on canvas B, and segments C on canvas C. I could draw them on the same canvas. I could even try different colors. I could get some effect similar to here, where some lines are blue, some lines are black, whatever. I just decided to do it like this to see the differences. I save the file, refresh the page. So same points, moving in the same exact way. 2 connections here, 3 here, and 10 here. You can see that this one on the right is fully connected now, but I would say there is no guarantee. If this component would just group together, would just cluster in a corner and the rest would cluster in another corner, there are 10 points in this component for sure, and 10 points in the rest from the 50. So all connections will be just between those components. This one now shows connected, and this one is almost connected. It has this here, and okay. All the time small things are appearing, disappearing. So now the question is, how can we leave the number of connections small but still guarantee a connected graph? This is it will give another type of effect. And to learn about these type of graphs, well, other graphs than the KNN graphs, we can look, for example, at this Delaunay graph. It's one way of doing it. Another type of graph that I'm actually going to implement today is called the Gabrielle graph. So what happens in this Gabrielle graph is 2 points, A and B, are going to have a link between them. So they will be considered neighbors if there is no other point inside this circle. So if I have a circle so that A and B are these opposites, this diameter opposites, if C would be inside this, another point, any point, if it would be inside here, then this connection would not exist. The previous one is very similar, but it doesn't need to be a circle like that. It can be any circle. A and B don't need to be diameter opposites. So if such a circle exists, then this line will appear. So you can see that this Delaunay, this Gabrielle is actually a subset of Delaunay. Here C would be inside this this circle from before, but it's not in this one. So they are subgraphs of each other. So let's try to implement this Gabrielle rule and form the neighbors in a different way and see what the result looks like. So let's say instead of doing the KNN 3 and KNN 10 there, I'm going to say segment C is empty, and on segments B I'm going to say get Gabrielle links, and this doesn't have a parameter. It's not going to look for neighbors in the same way. It's just going to check this circle criteria. So it's enough to just send the particles there.
Shouldn't we set the diameter of the circle?
Every pair of particles will need to be considered.
Yeah, but the diameter of the circle, isn't that a constant value?
No. So any 2 points that we have in the space will have their own circle.
Oh.
Yeah. So if we go back to this example here, okay, A and B have this circle here. They would be connected. A and C have this circle here. They wouldn't be connected because B and D are inside.
I got it.
Yeah. So let's see how it would look like if we implement it. This is actually much easier to implement than the KNN. So we have get KNN links there, and now we're going to have function get Gabrielle links particles, and we don't have any parameters here. This is a good thing. I'm going to copy here for loop for speed. So every particle, I'm going to check it against every other particle. So J here. And of course, similar as before, I could do the check that if I is not equal to J, so then we are talking about two different particles. So in this case, we want to know if our Gabrielle neighbors, particles of I and particles, okay, let's send just the index, it's smaller like that. Are Gabrielle neighbors particle I, particle J, and I will send the particles array to so that these indices make sense. So if they are neighbors, then I'm going to copy this code from here. Too many indentations here. I could have, if I is different to J and they are neighbors, so now I remove one level of indent there, and it's a little better. It's not the best, but let's leave it like this for now. I could separate some more of these into functions, but this function won't be much bigger than this, so small enough to have this escape. So usually I prefer to have 1-2 levels of indent, so now we get the third one here. Okay, so the segment, no neighbors this time, it's just particles A and particles J. So if they are neighbors, particles I and J, according to the Gabrielle rule, then we add this segment into the array and we will return segments. Okay, so we still need the function that checks if they are Gabrielle neighbors. And this one will have index A, index B, and particles or nodes, or yeah, this terminology should be, if I would write this code just for the purpose of these graphs, then everything would be vertices. I think it would be much clearer. Vertices and links or some graph terminology, but we will reuse this code in different places. So. Okay, so how do we check if they are neighbors? Well, if we look here, we need the point M, which is the average point between A and B. We have now this vector world, so M is equal to average particles of index A location and particles of index B location. So this is our M. And now we have to check if any other particle from this, except for A and B, is inside the circle. What is the radius of the circle? This is also important. So R is actually the distance from M to A, for example. So radius is distance M particle A's location. So going through all the particles, looking now for this C guy. So if even one of them is inside the circle, so distance from M to C less than R, no link, no deal. If all of them are going to be outside, then it is going to be a link then. I'm gonna name it C like in the slides. I should check here if I is different than index A and index B, because I'm looking for something else than A and B. So if they are different, then we take the particle, in this case I name it C, and I say distance is equal the distance between C and M. So whatever this distance is going to be here from C and M. If this one is smaller than R, then fine. But if even one of them is, if even one of them is smaller than R, so if distance less than radius, return false. So even one of them is going to return. This is not the best way to put here. These kind of return statements that are in the middle of the function, sure they work and you see them everywhere, but it breaks the sequential nature of the code here. So if you could make a condition, maybe this for loop could be a while loop, while you still go to particles and no particle inside found, it's going to be a clearer code that doesn't terminate somewhere in the middle of the code. I'm not going to do that now, but I more or less told you how to do it. Anyway, if this for loop ends with no return there, it must mean that all the points are outside of the circle. So they should be neighbors. So I'm going to save the file, close the PowerPoint, refresh the page. I think it works. So now the first one is the KNN with 2. The second one is this Gabrielle graph. So you can see that it is going to be connected all the time. This is one of the properties of the Gabrielle graph. And we don't have absurdly many connections here. Like they are much less than when we had the k equals to 10. You can still kind of count that, okay, this one has 5 neighbors, this one has 4 neighbors, this one has 4 neighbors. It may drop to 3 or something like that. So average is something, seems to be, this one has 2 neighbors, now 3, 4. So the k value would be, the number of links is more or less equivalent to KNN with k equals 3 or something like that in this case. So still keeping a few number of links, but everything remains connected. Now, there is this effect that links are appearing and disappearing all the time. And maybe you want to get rid of it somehow. I don't know how to deal with that. I could make them fade gradually. So instead of just removing the link, make its transparency go higher until it's completely transparent. That would be a less strong effect like what you see here. I could even keep the connections longer somehow, but it will start to have crossings, intersections. So think about it. If I just never update the links, okay, let's get back this global variable for segments. I'm gonna try to do something else. So I'm gonna say the global variable for segments is going to be equal to segments A if it's empty. So if this segment is empty in the beginning, it's going to become exactly the same as segments A, but it's going to stay like that. So after that it won't update anymore, no matter how the points are changing between them. If I take this and I draw it on canvas C, for example, I get a different effect. It doesn't work. Why? So, segments length is 0. So if segments is empty, so we defined it here as an array with 0 elements. So if this segments is going to be empty, it becomes the first time the segments are generated, and it stays like that because then it's going to have value, so it never gets updated. Then, so now it kind of looks the same, but all these links here that are appearing and disappearing are not changing anymore on the right side. So this graph is going to slowly start to become overlapping, points are overlapping, links overlapping. It's going to become slowly a mess. So if you want not to have links appearing or disappearing in your effect, you can do this, but then you have the problem of how to move the points in a smarter way so that it still looks cool, because slowly it starts to look like somebody's child made a bad drawing, like nothing, no structure really anymore. So I could get a better structure if I maybe make the points move less, or maybe the points would just orbit between their initial starting point. Then this kind of bad kind of visual effect wouldn't appear.
May I have a comment about this generation?
Yes.
Does it give you a good effect if your algorithm is such that you make the connections and start moving the points, and you are only checking the line-to-line intersections, and you resolve them locally so that every time it will resolve it? Will it give you a nice effect, or will
How would you resolve it locally?
You will exchange when you have two lines crossing, you resolve it by exchanging the edges, so it will open up.
I understand. So
maybe it's an avalanche effect, but I don't know.
Well, I believe it would be similar effect to the middle one, because you will still have edges that are appearing and disappearing suddenly.
Yeah, yeah.
So I would think that something like the second effect would appear. But it's a good point. It would be a little different, and I think because people see the points getting closer to each other, so they expect that something will happen to the lines that are crossing. So if you maybe make it fade the transition or whatever, expectation is there. I could recommend to you this book about maybe it's called 12 Principles of Animation. I'm not sure, I may be wrong, but it's made by the Disney guys.
I have heard about it.
Yeah, so you want to prepare the person that is seeing something for the action. That's why when you go to when you watch some cartoon and let's say somebody's about to punch somebody, it's not just this, it's like like really exaggerating that, okay, something is going to happen. So same here. I don't like in this effect personally that these links are so much appearing and disappearing there. I also don't like these intersections on the right. So I'm hard to please. But yeah. And finally, we're going to do something horrible today. And I'm going to show you what this XNN thing is. And I'm going to show it because it is our paper. And yeah, so the reason I want to present what this is these graphs are very computationally expensive to calculate. If I'm going to put here N100 maybe, it moves still quite okay. But if I'm going to put N1000, they tend to stop moving. Like even on my computer, nothing is moving. The frame rate is very, very low. It takes a very long time to process this complicated graph. For all of them actually, even the simple one on the left, because I'm having this complicated sorting function there, even though I just need a minimum 2. So I could make the first one more efficient. But now the points are not moving and my computer starts to make bzzz, this cooler engine is moving, so processor is really high. And the reason why I want to show this XNN is because it's a variation of the Gabrielle graph that has a lower time complexity when you calculate it. So let's try to see how that works. I'm not going to explain the algorithm because it would take a full hour. I'm going to do the dirty thing and copy everything. And I have to say, it's bad code. So don't look at this, it's just as an example. If you look at it, fine, but it's not the best coding example. I just want to demonstrate the complexity differences and how they look different slightly. So I just pasted about double the number of lines that we had previously. It has a bunch of components like this function create XNN that we're going to use. There is some clustering happening there, some splitting involved. I will explain how the algorithm works, just wait for me. It has k-means, you may know what k-means is. Many things I just pasted here. And yeah, don't worry about it. I'm never going to ask you about this at exam or something like that. So now in our functions here, I'm going to remove again the global variable for the segments. So this was just to demonstrate to you that in the last one the links start to overlap, and I find it not very useful there. So what we're going to do is for segment C, create XNN of particles. And let's lower a little bit the size n here. So 1000 is too much because the others won't move. So I hope this code works. Refreshing, it doesn't work. Oh yes, so this segment C is not being drawn anymore. I'm still putting these segments that is still defined there, so I didn't get an error. Yeah, JavaScript sometimes does print errors for these things. But now with the segment C into place there, it should show the XNN segments coming into the last canvas here. So I refresh the page. Okay, even more of this thing that I don't like very much. But it's some effect, and the problem of this algorithm is that it has quite much randomness into it. So if you would like to have more stable variant, you could try to run it a couple of times, like 2 or 3 times, and just add the links on top of each other. This is again something extra, but I will explain to you what is happening here on the right. So how this kind of graph is created soon. But first I want to demonstrate the speed of the method. So if I go back here and I say, okay, let's do this. Let's copy this, initialize them with empty arrays. So all of the segments are empty except for segments B, which uses the Gabrielle links. So now we only will get to see the Gabrielle links, and let's put the number of nodes back to 1000. So you see that the points are static, are almost barely moving, and there are some links that are appearing and disappearing there. This is because it's very, very, very slowed down. So you don't see much movement in the points themselves because my computer is really struggling now to display them. And instead of that, if I use the XNN instead, so I comment out the Gabrielle now, and I'm just going to get the XNN on the right screen. If I refresh the page, well, they are moving more, but not, I don't know how visible they are. Wonder if I would need to. I think you can see more movement. So the speed of the movement has to be low, or otherwise you don't recognize the motion. But definitely it's more movement than in the previous one. And the graph is still connected. So that property of the connected graph is still there. For visual point of view is not great. So many of the links are actually coming and going at the same time. So there is a randomness effect in this algorithm. And again, visually I would actually compute more graphs on top of each other and then combine the results. So now in Joensuu I can show the real-time effect, but in Kuopio it's not going to be very visible. So this is the problem. The graph, every time the frames change, is connected, is completely connected, but too many lines are becoming random. So I could call it multiple times and then in one frame just add up links from the multiple runs, and then this blinking effect would reduce. And time complexity wouldn't increase if I repeated a constant number of times. Maybe I can actually...
One moment, is it possible to add a time label to segment so that you are not refreshing it too fast so that it will not give this effect? It's like a lazy connection, right?
Can you repeat?
Yes, about this, if I understood, it's annoying to see the...
Well, for me it is. Maybe for somebody else it's not.
I mean, just for flashing lights, how about giving a time label for segments so that it will lag somehow?
Yes, that's what I was suggesting before. So, so that you keep it for a longer period of time. You give it a lifespan, kind of like our particles had at some point in previous lectures. Okay, but now I want to show you something, how this algorithm works, and I'm not going to take a very long time to show it, but I think it's important to demonstrate. So, okay, I'm gonna take here some paper link. Okay. I wanted to copy the link and paste it in the same browser here. So this is an application we made for demonstration purposes. The link to the paper is also there, but it's quite technical. The idea is to use divide and conquer. Well, I guess it's not divide and conquer. It's not divide and conquer. It's just a divisive algorithm. So what you do is you cluster everything into two clusters, whatever you have in the beginning, and then you make the connection. And then you start to split again the larger partition, and then again you start to make connections according to the Gabrielle rule. There may be a little bit variance. We have tested here some different type of connections, but here connection according to Gabrielle rule, the same thing with the circle more or less. So if the center point of each of these clusters, if they have another center point of some other cluster there, then inside, then it won't have a link. Otherwise, the link appears. And this thing just continues until you have no more points left. And because this is done in such a way that you are starting off with very few points and gradually ending up with every point in its own cluster, time complexity becomes logarithmic factor of the number of points. It's not just logarithm, it's a bit more than that, and there is also k-means clustering running here, so that adds also some time complexity. I'm not going to get into all the details, but in the end the result looks like this, and compared to Gabrielle graph, we have no missing links on this run. We have two extra links. So for example, this link here would not be in the Gabrielle graph. Probably this point would be in the circle or something like that. And this link here would not be in the Gabrielle graph, probably because of this circle in the bottom here. So it's an approximation of the Gabrielle graph, but you can calculate it much faster. That's the whole point of this algorithm, and I just shamelessly promoted the paper now here. So it's yeah. From visual point of view, I have to say that it's not great as such, but because it's a fast to compute method, you could run it multiple times. You could get a little bit of overlapping links there, and then this always coming and going links there won't be so many. So it could be used, I think so. Also combined with this kind of lifespan idea. Yes?
Sorry, one quick question about this result you showed. So from the way it works, it's clear that it's all connected points, but so you cannot remove all the Gabrielle segments from the cluster. It will break something. Is it not a good idea? So to clean up, it's not an option or not?
Well, if you try to clean up afterwards, then you're going to have to start to do Gabrielle tests between every pair of points, and that will be the same time complexity as just computing the Gabrielle graph in the beginning. So, of course, you could do filtering somehow, but it should be in a smart way, maybe.
Yes.
I don't know how to do it. But this is just something. So, if you ever need a graph that is connected and nearest neighbors are almost there, because what I really should mention about this algorithm is even if I don't move the points at all, but I just restart it, it may end up to a different result. So now you see this link is here and this link is here. Before I had the link here at the bottom. So this is because the way clustering works. So k-means clustering typically starts with a random initialization, and then it may converge to a different local optima. So clustering is not going to solve perfectly. It's NP-hard problem. And this is the reason why here my links are very much moving all the time. They are changing so drastically because even if the points don't move very much, some of the links will appear and disappear due to this randomness. I would say that even this effect with the blinking could be used in some situations. Maybe if you use some light gray or whatever as a background and you just want to show movement with some structure, then that can be used. But this lesson is more or less, so you know some of these things, but I won't ask you to do anything with these graphs. But I have seen more and more coming because they don't require sprites, they don't require images, and it can look quite nice in a background if you add maybe some blur effects, if you add some glows, if you add some kind of transparency or whatever, then it can look quite like this abstract art, moving art. But now I'm going to enable again segments A and B. And lower the number of points here to, let's say, 100 or 50, the way we started in the beginning. Refresh the page, and now it should work on all computers. And yeah, okay. I wonder what happens if I put gravity on. I'm gonna leave it as 0, 0, and I'm going to enable the code that updates the location also with respect to the gravity. But now the gravity is 0, 0, so it won't affect in any way. I save the file, refresh the page, and I get errors.
You have the comment.
You
there?
forgot it.
No gravity line has no.
Here?
Yeah. Just the 2 up.
Oh, yeah. This is just to see what happens. And I'm going to say here, because it's a global variable, g is equal to 0 on the x-axis and 0.01 on the y-axis. Well, not very impressive. Maybe you can make this kind of effect. Or, okay, still have a few minutes. I really have a feeling that I'm going to complicate myself here, but I'm going to make the particles teleport to the other side of the screen if they are exiting the screen. Kind of like this old, some version of the old Snake game, when you, Pac-Man game, it had some exit points and then you teleport on the other side.
I have a question.
Yeah.
On the third canvas, sometimes the graph is not connected, like we have some missing links.
Really?
See this?
Oh my. Then it has a bug. Okay. I will try to fix it. So it's part of this many lines of code that I didn't explain. I think that I made a mistake when it should be connected. So in this demo, you can see that it always has to be connected, because every time you are adding some connection between the clusters and the other group. But there may be a bug in that code.
That's why in animation we have suspensions of disbelief, this principle.
Oh,
we have
okay.
to believe it's connected.
Yeah, okay. I'm not gonna add the teleportation thing anymore. It's I really have a bad feeling about doing it, so I'm not gonna do it. It's because of these particles have the old location and previous location, so if I would teleport, the velocity vector is gonna change by 300. And I have a feeling everything will just collapse. I would have to take care of the velocity, keep it before teleportation, and reapply it after the teleportation. You can try.